Hello everyone. Here's a fun thought before we jump in. Have you ever looked at a tangled mess of wires and wondered, how on earth does anyone figure out what's what? Well, that's exactly why we use circuit diagrams, the secret language of electricity. Why did the electron go to school? Because it wanted to get a charge out of learning. Now, circuit diagrams are like maps for electrical circuits. They use standardized symbols to represent components such as resistors, cells, and switches so we can easily understand and analyze circuits without guessing. Instead of drawing messy wires glued to a table, we focus on the electrical connections using simple symbols that stay the same no matter how you turn or flip them. For example, a resistor is drawn as a zigzag line, almost like a tiny mountain range, and a cell looks like a pair of lines, one long and one short, the longer line marking the positive terminal. Let's dive deeper into the symbols we use in circuit diagrams. Imagine you're assembling a puzzle. Each piece has a shape, right? Similarly, each electrical component has a specific symbol that tells us immediately what it is. First up, the resistor, denoted by a zigzag line. Think of it as a tiny speed bump that resists the flow of electric current. The cell symbol looks like two lines, one long and one short, where the longer line represents the positive terminal, kind of like a plus sign hanging out. Then we have bulbs, switches, ammeters, voltmeters, and connecting wires, all with their unique notations. For instance, an ammeter is shown as a circle with the letter A inside and measures current, while a voltmeter is a circle with V inside and measures voltage. And here's an important tip. The direction of current in these diagrams is always taken from the positive to the negative terminal of the cell, like water flowing downhill from higher potential to lower potential. Knowing these symbols is essential because in exams or practical problems, you'll be expected to read, interpret, and even draw circuit diagrams accurately. So, think of these symbols as your circuit vocabulary, helping you translate electric circuits fluently. Now, let's talk about series circuits. They're like a single-lane road where all vehicles follow one after another. In a series arrangement, components like resistors, bulbs, and switches are connected end to end so the same current flows through each element. Picture a conga line dancing through a circuit. Here, the total resistance of the circuit is simply the sum of each resistor's resistance, so the equivalent resistance, let's call it our equivalent, equals R1 plus R2 plus R3 and so on. In circuit diagrams, this looks like several zigzag resistor symbols connected in a row, one after the other, as you might see in figure 11.6. When measuring voltage and current in such a setup, remember, an ammeter is connected in series to measure the current flowing through the whole line, while a voltmeter is connected in parallel across components to measure the voltage drop. This arrangement is neat and straightforward, but remember, the total resistance increases like traffic getting slower on a longer road. Knowing this helps us predict how much current flows and how devices behave in a series circuit. Switching gears, now let's explore parallel circuits. Imagine a multi-lane highway where cars split into different lanes. That's how current behaves in parallel circuits. In these circuits, different components, say resistors, are connected across the same 2 points, forming branches or forks. The voltage across each branch is the same as the source voltage, so we say voltage equals V1 equals V2 equals V3 and so on. Because electricity can take multiple paths, the combined resistance decreases. The formula for total or equivalent resistance, our equivalent here, is 1 divided by our equivalent equals 1 divided by our 1 plus 1 divided by our 2 plus 1 divided by our 3 and so on. In diagrams, these branches fork out from a common node and then rejoin, maintaining the same voltage difference as shown in figure 11.9. The current in the circuit splits among the branches according to each branch's resistance, governed by Ohm's law applied to each limb. The lower the resistance, the higher the current through that branch. Parallel circuits are everywhere, like in your home's electrical wiring, allowing different appliances to run independently without affecting others. Next up, let's look at how meters and bulbs appear in circuit diagrams and what they tell us. An ammeter, shown as a circle with the letter A inside, is always placed in series with the circuit so it can measure the current flowing through the components. On the other hand, a voltmeter, depicted as a circle with V inside, connects across components in parallel to measure the voltage difference. Bulbs, the source of light in many circuits, are symbolized as a circle with a cross inside. The brightness of the bulb depends on power, which is the product of current and voltage, expressed with formulas like power equals current times voltage, or power equals current squared times resistance, or power equals voltage squared divided by resistance. Switches, controlling whether current can flow, are drawn as a break in the wire with a little hinged line. Closed switch means current can flow, open switch stops the flow. Using these standardized symbols makes reading and building circuits quick and clear, almost like reading a universal language of electricity. Next time you flip a switch to turn on a light, you're actually completing a circuit exactly like the ones we draw here. Let's put all this theory into action with a simple example. Suppose you have a cell rated 6 volts, a resistor of 3 ohms, a bulb, a key which acts as a switch, and an ammeter to measure current. Your task is to draw the circuit diagram connecting all these. To solve this, we use Ohm's law, which states voltage equals current times resistance. Rearranged, current equals voltage divided by resistance. Substituting the values, current I equals 6 volts divided by 3 ohms, which equals 2 amperes. So, the ammeter in the circuit will show 2 amperes flowing. The power dissipated by the bulb can be calculated to power equals current squared times resistance, which is 2 amperes squared times 3 ohms, giving 12 watts. The diagram you draw will show the battery, switch, resistor, bulb, and ammeter all connected in series, forming a neat loop. This simple circuit not only illustrates how symbols come together to represent real connections but also how calculations and measurements tell us the behavior of the circuit. To wrap up, let's quickly review the key takeaways. In series circuits, the total resistance is just the sum of all resistances. Our series equals our 1 plus our 2 plus our 3. In parallel circuits, the equivalent resistance is less than any individual resistance, calculated as 1 divided by our parallel equals 1 divided by our 1 plus 1 divided by our 2 plus 1 divided by our 3. Power in components can be expressed in 3 related ways: power equals current times voltage, power equals current squared times resistance, and power equals voltage squared divided by resistance. Current is calculated by the formula current equals voltage divided by resistance. Remember, circuit diagrams use standardized symbols so anyone can understand the layout and behavior of circuits at a glance. Series circuits maintain the same current throughout with additive resistance, while parallel circuits have equal voltage across branches and allow current to split, lowering total resistance. Proper placement of meters is key. Ammeters go in series to measure current, voltmeters in parallel to measure voltage. Switches are your circuit's on-off controls. Mastering these basics forms the foundation for analyzing and solving complex circuits, especially in exams where accuracy and clarity matter most. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.